As a last subject for lecture number 3, we will discuss about relative motion. In this relative motion, we will have the assumption that we have translating axes, not rotating. There's no rotation here. What does relative motion mean? First, we need to define the absolute motion. The motion observed from a fixed frame is called absolute motion. Remember that we say there is this fixed frame on Earth, and this is the way we show it. There's this x-axis, there's this y-axis, and there's an observer at point O, and then this observer observes the motion of this particle as it moves in xy plane. And the type of measurement that is done with respect to this point O, which is located at the center of this xy plane that is fixed to the Earth, is called absolute motion. So fixed frame is commonly termed as primary inertial frame. The set of axes attached to the Earth in which we neglect the motion of the Earth. Okay, so this is our definition. In that sense, you can also make other type of definitions. For example, if you place an accelerometer at that point, the type of measurements it's going to get will be 0, or a gyroscope will get 0 motion if this frame is fixed to the Earth. Accelerometer, by the way, measures accelerations. Gyroscope measures the angular rate. So it doesn't move, doesn't rotate, it stays on its fixed location, this type of axis. However, if you're going to make the measurements for the motion with respect to a moving frame, then that would be called relative motion. And as a result of that, the type of measurements you do, for example, velocity will be a relative velocity measurement, acceleration will be a relative acceleration measurement with respect to this moving frame. Now, first, not to make things complicated, we will investigate this relative motion, okay, relative motion with respect to a translating, non-rotating frame. Now, why does it make things easy? Let's take a look at the drawing, and then we will understand why this type of thing makes our lives a little bit easy, this type of assumption of non-rotating frame. Here is the moving frame, small x and y axes. This is moving, there is this origin B, and this origin B moves. What is being observed here is point A, and the type of path that it does. Okay, so it moves in this path, let's say. And there's this fixed frame, primary inertial frame, the capital X and Y. And if this small x and y frame, the moving frame, does not rotate, then the axes definitions will not change. These unit vectors define the direction of the axes, I and j. Unit vector, again, let's remember that the magnitude is equal to 1, and this is only about the direction. Therefore, the unit vector that I will use for the capital X and Y axes will be the same unit vectors. I'm not going to use anything different. This will be I, this is also I with that bar, that arrow. This is J axis, so this is also J unit vector defining the direction of these axes. And this is going to make our lives easier, obviously, when it comes to differentiation. You don't need to use another frame, another unit vector definition during differentiation. However, in the later stages of this course, we will deal with this problem. So as a start, we only consider translating frames. And now this point A, this particle, can be observed from two places. One place is this B point attached to this moving frame. So you can assume that there's this A moving, and then there's this guy who's also in motion, who's also moving, no rotation. This guy is moving in X and Y directions but not rotating, and he is also observing point A, and the type of observation he is going to do will be defined by this vector of R, A relative to B, position of A relative to B. And then there is a second observer which is just sitting down. There's this guy who is sitting down, who is not moving, and also observing point A. the particle A. And the type of observation it is doing instantaneously is resembled by this vector RA, or you could have called this RA actual vector as RA relative to point O. And then point O is fixed, so we call this the absolute position of point A with respect to this fixed frame. And then the same observer can also observe the motion of this frame, and in that sense the motion of this B point, because it's just translating. He doesn't need to observe the rotation of the frame. There's no rotation. He's just observing the motion of the frame by taking a look at how this B point moves, and that is observed by RB. And you can also rewrite this RB as position of B with respect to O. And this is again an absolute measurement of point B, because the measurement is done via a primary inertial frame. So as a result of that, I can use my vector calculus here and resemble this RA vector in terms of addition of RB and RA with respect to B. So I get an absolute position equation by using these three vectors. So in the absolute position of A, RA, is defined by absolute position of B plus the relative position of A with respect to B. If I take the derivative of this equation on both sides with respect to time, then I get the absolute velocity of A to be equal to the absolute velocity of B plus the relative velocity of A with respect to B. And again, one more derivative would provide me with the information of absolute acceleration. And the absolute acceleration of A is equal to absolute acceleration of B plus the relative acceleration of A with respect to B. Again, these are all vectors, and vectors are free from any reference frame. Actually, you can resolve these vectors with respect to any frame, but at the end, because we have a translating frame, the same type of axes definitions can be used. What I'm trying to say here is, if I say RA is composed of RAX in the I direction plus RAY in the J direction, these are the components of this R vector, then the components of the RB vector would be resembled as RBXI, the same unit vector will be used in this definition, and RBYJ. And similar to that, I can represent RA with respect to B vector as RA with respect to BX times I plus RA with respect to BY times J. Same type of unit vectors could be used for defining all these vectors, and then the derivatives of these, obviously I and J direction doesn't change, so you'll get RAX dot, RAY dot, similar with these ones as you take the derivatives of these. However, as I told you, the vectors are free from reference frames. You can choose at any instant if it pleases you, or if it is natural for your problem, or if it's going to make your life easier. You can choose a different frame for velocity and accelerations, if you like, even for the position vectors. For example, you can use NT coordinates if you like. You don't have to use rectangular coordinates at that instant, or polar coordinates, if that will make your problem solvable. If you're going to use the rectangular coordinates, then this x dot that is presented here is actually what we have written out as RAB x dot, and y dot is RAB y dot. Okay, and then the double dots is the same idea basically. And like I said, you can use the NT coordinates if you like. If you like, you can use the polar coordinates in the definition of these axes, in the definition of these vectors. However, if you choose a certain frame for the absolute frame, you should not change that frame during the calculation. You should stick with that definition. The selection of the moving point B for attachment of the reference frame is arbitrary. Point A can be used as well for the attachment. So we can interchange the observation frame if you like. Let's say that instead of A being tracked, you might want to track point B. Okay? And then you have this observer at point A in that case. And you can define the absolute position of A and absolute position of B with respect to the axis. In that case, the equation will change into RB. The absolute position of B will be equal to the observation frame's origin's absolute position, RA, plus the relative motion defined from A to B in this case. So we write RBA. If you would like to change this definition, maybe you can also write RAB if you like. Or you could write that as AB. Different ways of defining the same type of information. Now if you take a look at this RAB and RBA definition, remember that we use this RAB in the definition of RA to be equal to RB plus the relative position of RB with respect to A. Now if you compare these equations, then you find out that RBA is actually the minus of RAB. That means in the opposite direction. So RAB is defined in this direction. I can show it like this. So this is the blue line is RAB from B to A. RBA is from A to B, or RBA can be resembled as RAB or AB vector in short. And then as a result of that, taking the derivatives of these equations, you'll find out that there's this negative sign for the relative velocity depending on the observation point. If the observation point is A, then you have this VB with respect to A. If the observation point is B, then you have this velocity, relative velocity, VA relative to B. Similar thing for the accelerations. Okay, so next we're going to have an example, a simple example, but it is a good example in terms of understanding what you can do with the frames. Now let's take a look at this example with the two cars. One car is moving in the circular path, and this is car A, and the other car is moving in the straight path along this direction. Now this has a velocity V, and this guy has a velocity of A. And car A is traveling with a constant speed of 60 kilometers per hour, so we know the speed of that. And then the radius of this curvature is 300 meters. It is a fixed radius. And car B is traveling by 80 kilometers per hour in this direction to the left. Now at this point you need to make a selection of your frame, how your axis will be. Maybe you want to select this axis as x-axis if you like, and then you might select this axis as y-axis. In this case, the z-axis is going inside the board. Okay, with this type of a definition. Or, let's get rid of these. You can select, oops, okay, this is VA. You can select the x-axis in this direction, and then y-axis in this direction. So this is something that you're used to. And as a result of that, the velocity B of B car is in the negative x direction. So if you want to resemble its velocity, it will be velocity of B with respect to this frame would be negative 80 I. The negative I direction. This is I vector. This is the J vector. Okay, if you choose this type of resemblance. Now this is the way that it appears in the PDF file. So I'm going to choose a different frame from this, so that you will see that you can actually choose different frames. Okay, so I will choose this frame as this is the x-axis, this is the y-axis. Okay? That's my choice, which will have a different intermediate steps, but at the end we will get the same answer. Now if this is x-axis, this is y-axis, then I can define the velocity of car B vector as 80 kilometers per hour in the I direction, positive I direction. Velocity of car A, okay, this is the velocity vector, so it will get two components with respect to this angle. This is theta and this is theta angle, right? This is theta, this is theta, this is theta. And as a result of that, it will be VA vector. In the x-axis, it will be in the negative direction. It will be calculated by using the sine. So it will be 60 kilometers sine 45 degrees in the negative I-axis, right? With respect to my definition, by the way. If you change this definition of the frame, it will change. This negative sign will change. In the y, it is in the positive direction, so it will be positive 60 cosine 45 degrees in the j direction. So far, so good. Let's read the question after this investigation. As this car passes through the center of the circle, so it's at the center of the circle, and there's a guy inside the car B observing car A, and car A is located with respect to car B by polar coordinates r and theta. These are r and theta values. And for this instance, we are asked to determine the relative velocity of A with respect to B. So to the guy that is sitting inside B car, what is the relative values for r dot and theta dot? Okay, VAB's representation of r dot and theta dot. Interesting question in that sense. What we can directly write out is we are trying to find out this VAB. So basically, we have this velocity of A, absolute velocity of A, that is observed from the velocity of from car B, so this is the observation frame, plus the relative velocity of A with respect to the observation frame. And as a result of that, you can say VAB is actually equal to VA minus VB. And I already have these vectors, right? So I can write out this equation and find out the VAB vector. VA relative to B, in that sense, will be negative 60, negative 80. So there we're going to have negative 60 sine 45 degrees negative 80. And that would be in the I direction, and then 60 minus 0, there's no j component of b, so that will be plus 60 cosine 45 j. That is our A relative to B velocity, and this is in the ij axis. Okay, so this is our relative velocity vector. If you want to determine the magnitude of that, and that is what is asked here, what you need to do is find this numerical value, square that up, find this numerical value, square that up, and then take the square root of that. So that would be VAB, that is equal to in the square root of VAB x squared plus VAB y squared. This is VAB x component, this is VAB y component. Okay, put it in this equation and then you will find this magnitude. Now for the r dot and theta dot, that's a different story. So let's work on it. Let's get some space for that. Now for r dot and theta dot, we need to take a look at the polar coordinate of this velocity, polar coordinate definition of this velocity vector. It will be composed of r dot in the r direction, ER direction, plus r theta dot in the E theta direction. Now the question is, There are these directions. Do I know these directions? Actually, I know these directions. ER and E theta are unit vectors again, and I can define these. If I can define these directions, then all I need to do is to find the projection of this velocity vector onto these axes. So that means what I will do for finding R dot, which is going to be VAB R component, let's say. And the way that you're going to calculate that is by projection. Remember that the projection is found by the dot product operation of vectors. Projection of one vector to the other vector. And you can interchange the multiplication order, by the way, for dot product. So we get a scalar, right? So VAB vector dot product ER will get me the result in the ER direction of the velocity. So I will get R dot information here. Similar to that, for R theta dot, what I need to do is take the dot product of VAB with E theta unit vector. And then I can divide this by R and I will find theta dot basically. So what's remaining for me to do is to find out these directions of ER and E theta. So for that, let's take a look at our sketch once again. In this sketch, let me change the color. In this sketch, with respect to the R theta components, my ER direction is this direction. Now let's take a look at how the theta changes. Theta changes positively in this direction as given in this question from the x-axis. So that means the E theta direction is this direction. Okay. Now I can represent ER and E theta based on this x and y axes. So based on I and j definition of my definition. Okay. In the numerical solutions you have a different definition, but I have changed already the directions. Right? There I have changed the axes formation for my solution. You can come up with your own solution as well. You can come up with a solution choosing, I'm going to call this x-axis, and I'm going to call this y-axis if you like. You can do a solution with this as well. You have to be consistent, by the way. If you choose this frame, you have to be consistent how you define these velocity vectors. But we are not going to choose this one. We have already chosen this xy axis, so I should be consistent with my selection of the xy axis. So with respect to this selection, the E theta direction will be represented by, maybe I can move up for some space here. Okay, that's good. Now E theta direction will have two components, one component here, one component there. Theta is 45 degrees, so it will be negative sine 45 degrees in the I direction. As you can see, its component is in the negative direction of y, that's why we get a minus sign. This is I. And the y-axis is in the positive direction, so it will be positive cosine 45 degrees j. And if you take a look at this magnitude here, if you do the necessary calculation, you will see that the magnitude is equal to 1, right? Sine squared plus cosine squared of the same angle is equal to 1, right? So that the magnitude is equal to 1. Then I can define ER similar to that. Now it's in the positive direction, so we get this cosine 45 degrees in the I direction. And the y is also in positive. This is the y part. This is the x part. This is cosine 45 degrees. This is sine 45 degrees. And that would be plus sine 45 degrees in the j direction. So at the end, all you need to do is now take the dot product of ER with the VAB vector, this vector. Okay, this is our vector. And find the resultant, and that will be equal to R dot. Then take the dot product of E theta with the relative velocity vector of A with respect to B, and then you will receive R theta dot then divide that by r and you will find the theta dot value. You have the numerical results here. Please do it for yourself as well, just to try my axes and see it for yourself. If you get the same answer, same numerical value, you should get the same numerical value. So this is the rest of the equations here represent what I have talked about. This is the definition of ER and E theta based on this definition of the frames X and Y. The type of definition we used in the problem that I showed there, the steps, is in this way, X and Y. You should get the same result if you be consistent in your selection of the frame. And as a result of that, ER is defined differently than what I did because this frame is chosen in this solution that is appearing in your PDF files. But at the end, the type of numerical results will be the same. So you get the dot product of this, and that will be equal to R dot. You get the dot product of this is R theta dot. So you need to divide by R to find theta dot value, which is already given over here as 0.108 radians per second.